Last week, we learned about the horizontal and vertical movement of concrete pouring and SRC columns in the base, and cranes for the construction of columns and towers. From this week, we will find out through the unique cantilever structure of Cctv and how it overcame the irregular load acting on the tilted tower. Cctv headquarters applied the diamond grid structure to overcome the disadvantages resulting from unusual shapes and loads. The diamond grid structure system is a combination of diagonal and grid, also called an ultra-large diagonal structural system. A diamond grid is a triangular module that uses beams and bracing members instead of a vertical column and is a structural system that resists vertical and horizontal loads. The diamond grid persists in transmitting the force of the column, allowing various elevational expressions in building compared to the existing system. The diagrid resists vertical loads through the compressive stress of the bracing member and the strati effect of the horizontal member, and the horizontal load is resisted by the tensile compressive stress of the bracing member in the strati model. When a load is applied to the upper part of the grid, the diagonal portion receives a compressive force and the lower member holds while receiving a tensile force. A large number of these models are arranged in the diamond grid so they make a structure that holds each other's loads and transmits the load. The resistance to the vertical load is affected by the sin value of the diagonal, and the resistance to the horizontal load is affected by the cos value of the diagonal loads. The horizontal vertical resistance of the diagrid is affected by the angle of the diagrid. If the angle formed by the diagonal member of the diamond grid with the horizontal line is zeta, how is the value of zeta of the diamond grid in this tower determined? To find out, we first need to define flexural stiffness and shear stiffness. Bending stiffness is a force that can withstand external forces that bend a material, and the optimal value for bending stiffness is obviously 19 degrees. The shear stiffness is defined as the force withstanding shear force as shown in the above equation, and the optimal zeta value for the maximum shear stiffness of the system is zeta when sin sine 2 zeta cosine zeta is at its maximum, that is about 35 degrees from the graph above. Therefore, the optimal zeta of the column for maximum bending stiffness is 90 degrees, and the optimal zeta of the diagonal for maximum shear stiffness is about 35 degrees, and the optimal angle for bending stiffness and shear stiffness of diagonal members of the diamond grid structure is expected to be in between. Let's look into an experimental case for a more accurate value of zeta. In a building with a size of 36 meters, 240 meters, and one floor of 4 meters, a diamond grid is installed for each value of zeta as follows. If the total height of the building is h and the width of the building is b, the aspect ratio of the building is 6.67 and the building is 60 floors, and each value of zeta is 34, 53, 63, 69, 76, and 82. The graph shows the result of measuring the horizontal displacement according to the value of zeta for each building as follows. As a result of the calculation, when the value of zeta was 69 degrees, the horizontal displacement value was the minimum. That is, it was found that the lateral stiffness was not very sensitive to the angle in the 69-degree region. Through this, the aspect ratio is 6.67, and in the case of a building with 60 floors, the zeta value is optimal at bigger than 65 and smaller than 75. Long buildings with a high aspect ratio tend to behave like warpage beams, and short buildings with a low aspect ratio tend to behave like shear beams. Therefore, considering that the optimum zeta of the pillar for the maximum flexure stiffness is 90 degrees, and the optimum zeta of the diagonal for the maximum shear stiffness is about 35 degrees, the higher the aspect ratio, the higher the optimum zeta value, and the lower the aspect ratio, the lower the optimum zeta value. Through the above experiment, let's predict the optimal zeta value of the diamond grid applied to CCTV headquarters. First of all, the height of CCTV headquarters is 234 meters and the width of each column is 52 meters and 59 meters. Since the aspect ratio of CCTV headquarters is 4.5 and 4, it is lower than the experimental condition with an aspect ratio of 6.67. Therefore, since the importance of bending for the overall transverse displacement is reduced than the experimental result, it can be predicted that the optimal zeta value will be less than 69 degrees. The actual aspect ratio was reset to 5 and readjusted, resulting in the following graph. It can be seen that when the aspect ratio is 5, the optimal value of zeta exists near 63 degrees. Since the aspect ratio of CCTV headquarters is 4.5 and 4, and respectively, the optimal value of zeta of the diamond grid applied to this tower is expected to be less than 63 degrees. If so, let's check directly if these predictions are correct. When the zeta value of the diamond grid applied to CCTV headquarters is measured through 3D modeling, 53.6 degrees and 49.1 degrees, respectively, it can be seen that this is consistent with the prediction. This week, we predicted the optimal angle of the diamond grid applied to the CCTV headquarters tower parts through the principle and experiments of the diamond grid and confirmed that this prediction is actually correct. Unlike the tower part diamond grid, which has a relatively uniform angle, it can be seen that the diamond angle of the cantilever beam is different. This is due to the difference in the force applied by the column and the beam. In addition, it can be seen that the diamond grid is not uniformly distributed, but the concentrated part and the part that are not are divided. Next week, we will present the diamond angle and the distribution of the diamond grid of the cantilever beam. Thanks for your attention.